Hi, welcome back to Statistics 1. We're up to Lecture 4, and the topic of today's lecture is correlations. Hopefully by the end of today's lecture, you'll see why correlations are incredibly powerful and central to statistics, but have also generated and are the source of a lot of controversy. So today's lecture is organized into 3 segments. I'll start with just some examples of correlations, so you get a feel for what correlations can do, what they're used for. And then in the second segment, we'll take a more mathematical approach. We'll go through the actual computation of the correlation coefficient. And then in the third segment, we'll step back, take a more conceptual view, and think about how correlations are interpreted. And there you'll see why and how they've generated controversy in some places, especially in the social sciences. So let's start with segment 1. So in segment 1, I just want to present some examples to give you the concept of correlation and to get the discussion started. The important topics to take away from segment 1 is just, again, what is a correlation? What are they used for? And I'd like to demonstrate a new graph, scatter plots, and show you how scatter plots can be useful and how they can tell us a lot about what's going on in our data. Okay, so a correlation, just simply defining correlation, is a statistical procedure that's used to measure and describe the relationship between 2 variables. And you can think of correlations, we're sort of at a point in this course where we're on the cusp of descriptive statistics and inferential statistics. You can think of correlations as both. So sometimes a correlation can be thought of as just a descriptive statistic. We're just describing the relationship between 2 variables in a sample. Or we might be using it in inferential statistics. So we might be computing the correlation coefficient in a sample and then trying to make an inference about the relationship between 2 variables in a population. Hopefully this is review, this second point, but just to be clear, correlations can range from +1, which is a perfect positive correlation, to -1, which is a perfect negative correlation, and of course 0 means no relationship between the 2 variables at all. So to take an example from my own research, we know that scores on tests of short-term memory capacity, or what I call working memory capacity, are strongly correlated with scores on standardized tests, like the SAT. So here in the US, the SAT is used by admissions officers to decide who's admitted to certain colleges. So if I know a person's score on a working memory task, then I could predict how well they might do on the SAT. And if we know how well someone has done on the SAT, then we can predict how well they might do in college. The correlation between SAT and first-year grades in college is modest, but it is there and it's significant, which is what the SAT uses to justify their existence. So that's best illustrated using a scatter plot. So what I've done here is I generated data in R, and I'm showing you the actual function that I used in R. So now that you've had some exposure to R, I'll start doing that and introducing these functions in the lectures. So to get the scatter plot, I just used the function plot. My variables were SAT and WMC for working memory capacity. And the variable that I want on the y-axis comes first, so it's ply y tilde x. And in this example, I want to use working memory capacity to predict SAT. So the predictor variable, or x, is plotted on the x-axis, and what we call the outcome variable is plotted on the y-axis. So what you see here is a modest positive correlation. So the correlation is a positive 0.22. What this line represents here is known as the regression line. And that tells us how strong the relationship is between working memory capacity and SAT. What it illustrates is as working memory capacity increases, so does SAT score. But the correlation here isn't that strong, and it's actually not consistent with prior research. This is much lower than what I've seen in my own work and what lots of other people have seen. The correlation is typically around 0.5, even 0.6 in some instances. So let's talk about some of the reasons why this correlation might be a little low. Well, let's go back and look at histograms. So if you remember from lecture 2 on descriptive statistics, one way to look at your data is to look at histograms. So what I've plotted here is a histogram of the SAT scores. And the maximum score that you can get on the SAT is 2,400. There are 3 sections where the maximum is 800, so the 3 add up to 2,400. And getting 2,400 is exceptional. That's a perfect score on an SAT. Now let's look at this distribution. See a lot of students way up here at the top. And that's not surprising because these data are based on data I collected at a prestigious university that I will not name, not Princeton, but a prestigious university here in the US. So the students were pre-selected on the basis of their cognitive ability, and so it's not surprising that we have a negatively skewed distribution with respect to SAT scores. Also, the working memory score, not quite as bad, but still sort of skewed. Since we don't have the full range of ability on either working memory capacity and especially SAT, that's what's driving down this correlation relative to other correlations that we've seen in the literature, because those correlations were based on samples that had a broader range of cognitive ability. More variance allowed for more covariance. So that leads me into my several statements of caution when looking at correlations. So caution number 1. I said we can predict people's scores. If I know their score on X, I can predict their score on Y, right? Well, obviously that depends on the magnitude of the correlation. If there's no correlation, I have no basis for prediction. But if I have some degree of correlation, then my predictions get better to the point where if X and Y are correlated at 1, then I could get perfectly accurate predictions. Now, the magnitude of the correlation is going to depend on a lot of factors, right? So 1, it will depend on the reliability of the variables, so the reliability of X and the reliability of Y. In lecture 5, we'll talk about measurement theory in psychology and how we determine if a particular measure is reliable or not. But just remember, the magnitude of this correlation will depend on reliability. Easy way to remember that is the reliability of X refers to, well, will the score be reliable or consistent over time? Think of just a scale used to measure weight. Is the scale reliable? Well, get on it one time, you get your weight, get on it again. Is it the same weight? Is it consistent? Yes, it's a reliable measure. If a measure X doesn't correlate with itself, meaning shows low reliability, how can it possibly correlate with anything else? So the magnitude of correlations critically depends on the reliability of our measures. And in lecture 5, we'll talk a lot about assessment of reliability. But the magnitude of correlation also depends upon sampling, and that's what's illustrated in this first example. You need a random and representative sample to get an accurate correlation estimate. What happened here is I didn't have proper sampling of a range of cognitive abilities, so my correlation was attenuated because I had a restricted range to people who were high on the SAT. So make sure you have random representative sampling, particularly for correlations. Another caution is with respect to the validity of the prediction. Is it valid to make this prediction? That too will depend on the validity of our measures. And again, in lecture 5, we'll talk about validity in more detail. Here, we're going to talk about several assumptions, statistical mathematical assumptions, underlying the correlation approach. And I'll dig into those in more detail in segment 3 of the current lecture. And perhaps most important, and this is the one point that I'd like to get across to many of my friends and family members who don't have a background in statistics, when they start to get into arguments about correlations that they see reported in the news or that they read on the internet. The correlation coefficient is a sample statistic. It represents the relationship between X and Y at the level of a sample, at the level of a group. It does not apply to an individual, right? So if the correlation between SAT and college GPA or performance in college is strong, as long as it's not 1.0, that means for any one individual, they could buck that trend, right? Doesn't mean that they are right on the regression line. Let me be more accurate. It doesn't mean that everyone is right on the regression line, unless the correlation is 1.0. Okay? So keep that in mind as you think about correlations. They are statistics that describe the relationship between two variables at the level of a sample, not within an individual. An individual may fall right on the regression line, may not. Okay, let's move to a more serious example. I have 2 more examples, one serious, one fun. First, the serious example. And this has to do with the birth of modern intelligence testing, which actually came out of World War I. So the United States became officially involved in World War I in April of 1917. And before that, President Woodrow Wilson successfully kept the U.S. neutral, and he really tried to keep the U.S. out of the war. For 2.5 years, he was successful at that. But eventually, it just became inevitable, and the U.S. went to war in 1917. The problem with that is the U.S. really wasn't ready for the scope or scale of what they were getting involved in. So that presented numerous challenges to the military, to the country as a whole. But I want to focus on one particular challenge and talk about how it led to intelligence testing. So a challenge for the U.S. military was how to recruit this large number of men. The U.S. military grew tremendously during this time, and then how to assign them to the right positions. So people come in with different sorts of talents, different sets of skills. So to sort of maximize the efficiency of the military, you want to get people in the right positions. And specifically what I want to focus on here is they had to make decisions about who should be designated as officers or designated ready for officer training, and those who weren't really up to that. So how do you make those decisions? Well, the U.S. military called on prominent psychologists of the day because by historical coincidence, the turn of the century saw sort of the birth of modern intelligence testing as we know it, but in developmental psychology with children in school. But the U.S. military was aware of this work, and they called on psychologists to develop intelligence tests for adults that could sort of tell them about the sets of skills and aptitudes that different men had so they could assign them to the right posts. The first test developed by the U.S. military was called, appropriately, the Army Alpha Battery. And what was new about the Army Alpha was they designed a test that could be administered quickly to a large number of people. What that meant is they had multiple choice questions and short answer questions. This is different from a lot of the developmental work that had been done up to that point, which is more geared toward an individual child and one-on-one administration of a test. The contemporary equivalent of that, the US military still has this sort of testing, is known as the ASVAB. And some of you who are taking this in the US, maybe you've taken the ASVAB. Robert Yerkes, who's a professor of psychology at Harvard, was one of the psychologists involved in this and one of the leaders of this effort. And he argued that the test measured native intellectual ability, meaning that it wasn't biased by cultural background or ethnic background. And that was a very controversial statement and led to a long debate in psychology and in the social sciences in general. And a lot of research since then has shown that he was flat out wrong. Okay, so this initial test, the Army Alpha, was clearly culturally biased. But the question I want to pose to you, and I don't have a slide after this one, I just want to pose this question is, in the context of correlations, what type of statistical evidence would you look for to either support or refute Yerkes' claim that it was culturally biased, that it wasn't culturally biased? What type of analysis, what type of study could you do? I'm just going to pause for a moment to let you think about that in the context of correlations. Right. So I just taught this same material in a course here at Princeton, and I posed this question to the students. And the initial answer was, well, if one group did worse on the test overall than another group, then it's biased. Okay, but that's not enough, right? It could be that two groups differ in their readiness to be officers or to go to officer training school. What we need more than just a difference between the groups is a difference in predictive validity. That is, a difference in correlations. That is, if the test is predictive of how well the officers do on the job or how well the soldier does in officer training, if it's predictive for one group but not for the other, then we see evidence for bias. Because what it's saying, what the correlation analysis is showing, is that this is a reliable measure of something for one group, but it's not a reliable measure for another group. And that kind of correlational analysis is what was done after Yerkes introduced the test to really drive home the point that it truly was culturally biased. Okay, enough serious stuff. Now let's move to a fun example. Statistics are used a lot in baseball. And forgive me again if you're not in the US, I'll tell you a little bit about baseball so you understand this example. This is a big field, actually, and it has a name. It's called sabermetrics. So again, for those of you not too familiar with baseball, I'll tell you just a couple things so you can understand this example. And for reference, this is a picture of Lou Gehrig, one of the greatest baseball players of all time. So a few terms that I'll use. One is a plate appearance. In baseball, a player gets up to bat, and that's what I was showing you there with Lou Gehrig. The pitcher throws the ball. They have to try and hit the ball and get what's called a hit. So if they hit the ball and they get on base, that's a hit. Baseball statisticians make a difference between a plate appearance and an at-bat because there are other things that can happen on the field other than the batter making an out. And if that's the case, the batter shouldn't be penalized. So the batter, it doesn't count as an at-bat, but it counts as a plate appearance. There are many things that could happen. The batter could get a hit. The batter could walk. That's when the pitcher throws 4 balls. The batter could get hit by the pitch, in which case they get to take base. Or they could hit a sacrifice fly, meaning they could hit a long ball out to the outfield, but it's caught for an out, and one of the runners could advance, which is a good thing for the offense, but the batter doesn't get to get on base and has to go back to the dugout. Okay. So the main statistic that most people look at for how well a player is hitting is their batting average. And their batting average is very simple. It's just the number of hits they have relative to the number of at-bats. That's pretty straightforward. And actually, a lot of us here in the US, we played baseball as kids, and that was probably, or you play softball. That's the statistic that a lot of us keep track of, or kept track of when we were kids, is what was your batting average. It turns out there's another statistic, though, that is actually more informative, and it's called on-base percentage. As I said, there's a lot of things that can happen when you're at bat. You might get on base because you got hit by the pitch. You might get on base because you walked. And you should get credit for that in terms of contributing to the offense. So that's called on-base percentage, just how often do you get on base. That's hits plus walks plus hit by pitch over all the other possibilities. So the question is, which statistic is a better predictor of a player's contribution to the offense, batting average or on-base percentage? We already know, because I'm giving you this example, that on-base percentage is going to do better, right? But that wasn't known in Major League Baseball, the professional organization of baseball here in the US. That wasn't known until the mid-'80s. And even if you're not familiar with baseball, you may have seen the movie Moneyball, which talks about this, and talked about a general manager named Billy Beane who used this to evaluate players and to pick players. I hated the movie Moneyball. Even though I love statistics and I love baseball, the movie hyped the contribution that Billy Beane made to using statistics to evaluate players. They basically made it look like Billy Beane came up with this idea of on-base percentage. Lots of people recognize how useful on-base percentage is way before Billy Beane came along. In fact, it was adopted by the Major League Baseball Association in 1984. In 1984, Billy Beane was still a player, struggling in the minors. He played for the New York Mets minors, and he shared a hotel room with this guy, Lenny Dykstra, one of my favorite players of all time, because he was just crazy. And they played together in the minor leagues, and everyone just thought that Billy Beane would be the next outfielder promoted to the majors for the Mets. No one expected Dykstra to be the player. But Billy Beane was too analytical, and now here he is doing statistics. Dykstra wasn't. So Dykstra was 5'10", 180. Beane was 6'4", 210, and Beane was faster. Yet Dykstra was promoted, went to the majors. 2 years later, the Mets won the World Series. Dykstra won the championship. Beane never really amounted to anything as a player. And I love Beane's description of Dykstra is he's perfectly designed emotionally for baseball. He has no concept of failure. The point is that Beane was too analytical at the plate, which makes for a bad hitter. That's why I don't play baseball. You just watch. So who invented the on-base percentage? If you're really into baseball like I am and you want to look into this more, look up Bill James, not William James. That's the father of psychology. Bill James, the father of sabermetrics. Okay, back to the example. Long tangent, sorry. So we can answer the question by looking at what is the correlation between runs scored and batting average, and what's the correlation between runs scored and on-base percentage. So I did that just taking a small sample of data. I took all the information from the New York Yankees 2011 season. I picked out the 10 top offensive players from the entire team, and I just analyzed the data. So what you see here, again, I used the plot function in R. R stands for runs, AVG for average. And what you see is a nice positive correlation between runs and batting average, 0.4. But let's look at on-base percentage. Now we see a correlation of 0.72. So clearly, on-base percentage is a better indicator of someone's contribution to the offense than simply batting average. So this was a step forward for Major League Baseball in how they could evaluate players, is getting a variable that's a better predictor, and they learned that by looking at correlation analyses. To sum up this segment, what I want you to take away is just the concept of correlation, what they're used for, and how we use scatter plots to evaluate correlations and see where correlations might be going wrong or where the strength is coming from.